To our lecture series on algebra. Today I'm taking the Unit 9 that has to do with binomial theorem. Again, my name is Reda Lesig and your lecturer for algebra or calculus 1. Under binomial theorem, we are going to take just 3 sub-outlines, that is introduction to binomial theorem, the coefficient and the number of terms in an expansion. But with this first video, I'm taking that of subunit 1 and subunit 2, and I'll take the last video on the number of terms. Thank you very much. So let's quickly look at what we have for the introduction. When we say binomial or you hear the word binomial, it should ring a bell right from polynomials. In polynomials, the binomial has 2 terms. We also did operations of polynomials. We can add, we can subtract, we can multiply, and we can divide. We've gone through that. If we want to stay close on the multiplication aspect, and I want to expand certain things, you know that a plus b all square is the same as a plus b and then a plus b. And I'll end up getting this value. If I want to the power cube, what I'll do is to multiply this part by what? A plus b. And I'll get this answer. If I have to the power 4, what I'll do is to multiply this answer I had here by under a plus b to get this answer. If I have to the power 5, I'll simply have to multiply my 4th here by some a plus b to get this answer. And that is simply what I'll be doing. You would realize that the calculations or the expansion gets longer and longer as we proceed, or the terms increases, and this can be quite cumbersome. If I'm supposed to find a plus b to the power 15, it means I'm going to multiply a plus b by itself 15 times to get what I need. Would that be helpful? No. And so you want to think critically and look at a certain pattern in the expansion. If you're able to see the pattern, good for you. If not, it is still fine. This pattern is what we call the binomial theorem. It says, since I'm a binomial term and you're expanding me, I have something to help you expand. Let me see if I can quickly see a pattern. I see square here, square here. I see cube here, cube here. I see to the power 4 here, to the power 4 here, and to the power 5 here, to the power 5 here, corresponding to the index of the expansion. That's some term there. So let's quickly look at what binomial theorem will help us to do if we don't want to go through keeping by expanding by number of terms. So I have it on slide 4. The binomial theorem helps us to expand an expression of this nature, a plus b to the power index n, which is also given by this or that. The difference here is here a is taking k and b is taking n minus k. When I move to the next part, I have n minus k and then k. They are the same. The index are just switching positions, but they are the same. Okay. And then we have our nk. It says it's a positive integer. I guess you know what integers are. 1, 2, 3, but they are positives. Okay. This is also called the binomial coefficient. Don't confuse the binomial theorem or expansion with the coefficient. The coefficient is part of the binomial expansion. The coefficient is given by the nk. And I'm sure you've seen this guy somewhere. Where did we see it? In permutations and combination. So you want to ask yourself, where would this fall? Is it permutations or it is combination? You realize permutations has to do with ordering. Combinations, the order do not matter. So that is the binomial coefficient. And so let's move straight into the coefficients and see what we can do. Given in slide 5. I asked the question, where would the nk fall into? If this is the formula for the NK, what do you think is correct? Is it permutation or it is combination? I would allow you to answer this question in the comment section. Per the formula, is it permutation or it is combination? If you're able to figure it out, that is fine. Now if you want to find the coefficient in the expansion here, permit me to move up. We have 2. Let me use a different color here. You see 2, you see 3, I see 4, I see 6, I see another 4, and then the coefficient here is 1, and then so on and so forth. If you want to see how this expansion is done, we can use the coefficient of a pattern. The pattern is Pascal triangle. Let's see how the pattern works. If I have the first exponent 1, it says all the border lines are 1. So from here in the Pascal triangle, all the elements on the border are 1. And what happens in between? In between is the sum of the numbers just above it. The sum of the numbers just above it. So let's see how we can do it. If I move to this form, this at n equal to 1. When n is 2, I have 1 at the border, and then I'll have 2 here. No, let me just be okay. If I have 1 at n equal to 2, I have 1 at the border here, 1 at this border, and add these 2 terms to get 2. When I go to n3, the border is 1. When I add these 2, I'm going to get 3. I add here, I'm going to get 3, and then 1 remains. So this at when the index is 3. This when the index is just 1. When the index is 4, so this when the index is 0. When the index 4, I have 1 here. This is 4. 3 is 6. 3, 1 is 4, and then the border 1. When n is 5, I have my border to be 1. When I add this, I have 5. 4, 6 gives me 10. 6, 4 is 10. 4, 1 is 5, and then the 1. We are adding the sums of the above terms. When n is 6, I have my border 1. 5 plus 1, 6. 6 plus 10, 15. 10 plus 10, 20. 10 plus 5, 15. 5 plus 1 is 6, and then the border 1. Let me take the last term. When n is equal to 7, my border is always 1. Then I add the inner terms of the above. So I get 7 here. Here 21. 15 plus 20 is 35. 35. 15 plus 6, 21. 6 plus 1, 7, and then the border 1. This is how the Pascal triangle behaves. And with this, I can simply find a plus b all square. I can easily find a plus b all cube through to a plus b to the power 7 using the Pascal triangle for the coefficient, and that is all. That is not enough. You want to go through some properties to make sure that your expansion is correctly done, and that is on slide 16. Properties of the expansion. The first property says if I want to find the number of terms in the expansion, it is given by n plus 1. This is simply saying that if I have a plus b to the power 2, my number of terms will be 3 because it's n plus 1. If I have a plus b to the power 4, my number of terms will be 5. If I have a plus b to the power 6, I'm expecting 7 terms in the expansion. A plus b to the power 20, I'm expecting 21 terms in the expansion. Again, permit me to move back here and then see. If I have to the power 2, I expect what? 3 terms. Do I have the 3 terms? Yes. Term 1, term 2, term 3, and so on and so forth. That is what it implies. Okay, I'm still here. That is the first property. The second property says the first term would always be, so let me clean these things here so I can keep explaining them. If the first term is always a to the power n, and then the last term is b to the power n, which if you move back to the expansion, you would realize it. This means if I have a plus b to the power square, my first term will be this, my last term will be that. A plus b to the power 6, My first term will be 6 plus some terms, my last term will be 6. If I have a plus b to the power 15, my first term will be a to the power 15, and then my last term will be b to the power 15. That is what this terms or property implies. I hope that is well understood. These properties are very important. Again, I'll clean this. The third property says that as the index of A increases, the other decreases. Or you can also say that as the index of A decreases, B should increase, in that form. That is not all. I want to add two properties. So I'm looking at 3 and 4. The 4 says as one increases, the other decreases. And 3 says that the sum of the indexes must be n. This is to say when I add whatever power I have on A and whatever power I have on B, they must give me n. This summation here must be n. So let's take a quick examples or explanation. So if I have A plus B to the power 2, I know my first term will be 2, means my B should be 0. I know my last term will be A to the power 0 and B to the power 2, and then there's a middle term here by the Pascal triangle. So as A increases, B decreases, and then the index is 2 here. The index here when I add is 2. Let me take one more thing. Assuming I have 8 plus B all cubed, it means if A starts from 3, B will start from 0, plus A will start from 2, B goes to 1, A goes to 1, B goes to 2, and then A goes to 0, B goes to 3. When I sum this, guys, I have the index 3 here. If I sum there, I have 3. If I sum this, I have 3. If I sum this, I have 3. The other rule says that as A increases, let's look at the index of A. It was 3, it came to 2, it came to 1, it came to 0. The index of B, it started from 0, it went to 1, it went to 2, it went to 3. What do you see? As this was decreasing, this guy here was increasing. And that is it. Again, these coefficients are from the Pascal triangle. You don't forget that. Let's quickly take examples. I'll take 2 examples and then I end the session. Example 1. We want to find the binomial expansion. I want to display all the examples. The solution for example 1. That's quite long. That is on slide 7. What is wrong here? I'm supposed to expand to the power 5, but in solving I use 3. Okay, let's just go by 3. Okay, let's just go by 3 to make life easier. If I want to expand this, I have this formula to use. I want to go by k and then n minus k. They are all correct. Or you go by a k minus n minus k and then b to the power k. These are all correct. And so it says that equal, there are certain things you want to find. You want to find what is n. In the preamble or in the question, n is 3, a is x, and then b is 3. Yeah, that is it. N is from here, please. So by the formula, it means k is going to run from 0 to 3 here, and I have 3k, x to the power k, and then 3 to the power 3 minus k. I'm doing a substitution, please. Assuming I don't know about the Pascal triangle and all that, this is how I would have expanded the whole series. I'll start from at k equal to 0. Then I'll have it as 3, 0, x to the power 0, right? And then I'll have it as 3 to the power 3 minus 0 is still 3. I don't want it this way, so let me change the formula. It's still the same thing, please don't worry. I want to use n minus k and then k here. So n minus k, that is 3 minus k, and then k. Don't forget I said they are all correct. So I can have it as k and then bn minus k. Okay. So it means I have it as 3 x to the power 3, and I have 3 to the power 0, plus at k equal to 1, wherever I see k I put 1, 3 1 x to the power 3 minus 1, which is this, and then 1, plus 3 2, that is at k equal to 2. I have x to the power 3 minus 2, and then 3 to the power 2. And I'll go to at k equal to 3. Don't forget k is running from 0 to 3. So I have 3 3 x to the power 3 minus 3, and then 2 3 to the power 0. Is that correct? No, 2 to the power 3. Yeah. This is what I have. If I want to simplify further, I have 3 0 x 3 3 to the power 0. I have 3 1 x to the power 2 3 to the power 1. And I have 3 combination 2 x to the power 1 3 to the power 2. 3 combination 3 x to the power 0 3 to the power 3. We want to verify the properties here. Let me write this. 3 combination 1. The property says that first, my number of terms should be n plus 1. It means I'm expecting 3 plus 1, which is 4 terms in the expansion. So you check, do I have 4 terms? Term 1, term 2, term 3, term 4. So this is satisfied. The second thing is saying that my first term would always be to the power n, and my last term will also be to the power n. So let's verify that. The first term, my a is x to the power 3, my b is 3 to the power 3. It is from here. X to the power 3, because 3 to the power 0 is 1. X to the power 0, and have this. So this also satisfied. The property 3 says that when I add these indexes, I should get n. So let's verify that. If I want to verify it, you realize that this and this gives me 3. This plus this is 3. This plus this is 3, and this plus this is 3. And so this is also satisfied. Then the fourth property I want to verify is that as the index of A increases or decreases, the index of B must increase. Or as the index of AN increases, the index of Bn must decrease. Let's verify from the answer. What do you see for x to the power n? It is moving from 3, it went to 2, it went to 1, it went to 0. And that of 3, it moved from 0, it went to 1, it went to 2, it went to 0. As this was decreasing, this guy was increasing, and so it is also satisfied. This is how you check the properties. Okay, then the fifth one I want to see is the coefficient, the binomial coefficient. That is from your nk. You can always get that from the Pascal triangle. So from the Pascal triangle, I know that my first coefficient is 1 here and then 1 here at the boundaries. The inners, I know there's going to be 3 and then 3. That is when n is equal to 3. If I'm right, you check, you verify that for me. So this guy here is going to give me 3. This should give me my 1. The coefficient here should give me 3. The combination here should give me 1. And that is how you get your coefficient from the Pascal triangle. Alright. Let's take the second example quickly. I hope this has been helpful. In the second example, I have slide 8. There's 1 2 3 4 5 6. Okay, let me see. 1 2 3 4 5. There are 5 trials. You want to choose one of it and then just check the answer. For simplicity's sake, I'll choose the first one. I'll choose the first one to help you out. And so I know this is the same as a to the power n minus k, and then b to the power k. Right, what is my n? My n is 3, my a is x, my b is 1. This is just like the first example. And so I know I'm going to run from n to k from 0 to 3 here, a to the power 3 minus k, and then b to the power k. This will be my expansion. But let me do the substitution quickly. This is the same as x, and this is the same as 1. Okay, so it means that how many terms do I expect? I expect 4 terms. Why? Because my index is to the power 3, so 3 plus 1 giving me 4 terms. And how would this look like? If you want to be smart with it, you know that this is going to be 0 combination 3, x to the power 3, 1 will be to the power 0, because the index must add up to n, plus 3 combination 1, x to the power 2, 1 to the power 1, plus 3 combination 2, x to the power 2, 1 to the power, I've moved from 2, so x to the power 1, 1 to the power 2. You realize that the k moves with the k here. Whenever you choose a value, k moves with the second one, k. And so 0 here, 0 here, 1 here, 1 here, 2 here, 2 here. Am I done with the terms? No. Plus 3 combination 3, x0, 1, 3, because there's 3 here. The index must add up to 3. The index must always add up to 3. And then you know where to get these ones. They are from the Pascal triangle. Or you can use the formula nk equal to n factorial k factorial n minus k factorial to get this coefficient. And all the other properties will be satisfied. Trust me. I expect 1, 3, 3, 1 with the certain this computed. Okay, if I want to go on and try for let's take 2x plus 1, 6, or 2x, let's take the 2x, 2x minus 3, 2x minus 3 all to the power 5. If I want to solve this, I know the same as summation a to the power nk, a to the power n minus k, b to the power k, where k runs from 0 to n. So you ask us, so what is my n? It is 5. What is my a? It is 2x. What is my b? It is negative 3. Don't forget the expansion is a plus bn. This means that your b is negative 3, please. This means I'm supposed to get expansion of this form. Summation 0 to 5, 5k, 2x to the power 5 minus k, times b, which is negative 3 to the power k. That's how the expansion would be. I'll go to the first few terms. To be smart enough, I know I'm going to have the 5 combination 0, 2x start from 5, negative 3 will take 0, because the index must add up to 5. But you know how many terms do I expect here? I expect 6 terms. Then I move from 0, I move to 1. And then my 2x will now reduce to 4. My negative 3 will increase to 1. So as 1 decreases, the other increases. Then I'll move to, from 1, I have to move to 2. And then my 2x will reduce to 3. My negative 3 would increase to 2. I move to combination 3. Don't forget k is running from 0 to what? 5, please. So 3, 2x would decrease to 2. Negative 3 will increase to 3. Plus 5 combination 4. My 2x now reduces to 1. Negative 3 would increase to 4. And then the last term is 5 combination 5. 2x reduces to 0. Negative 3 increases to 5. My conditions would all be satisfied. This is 5. This is 5. This is 5. When I add this, guys, I'll get 5. Again, your combinations are from the Pascal triangle. I have my 6 terms. My index are, let me do my conditions. I have my 6 terms given. My order as 2x was decreasing, the negative 3x was increasing in the index. You want to check that. Again, my first term would be 2x to the power 5. My last term with negative 3 to the power 5. You can verify from this and then that, because negative 3 to the power 0 is 1. That is not all. You realize that when I add the indexes of 2x, whatever I had here, and then the index of whatever I had here, they would always add up to 5, and so on and so forth. So this is how you verify your properties. You take your time and then you go through the lecture video for me. Okay, now the last thing for the day, that is the most interesting thing of all the series, is on the problem of the day. We want to see how we are applying our binomial theorem. Isn't that fascinating? It is. In this problem, we were given a genetic mutations in humans. If you read the preamble very well, I want to extract my information. Let me reduce this so you can see the problem of the day very well. It is looking at some genetic mutations in humans. You want to read on this. The image should tell you what mutations are. Some deficiencies in human. Either you have the mutation, yes, or you don't have the mutation, no. If it's yes, I'm assuming it's a success. Not success in a positive way, but you have it. If it's no, it's a failure, you don't have it. In the question, we are given some probability. Let me use S for success and F for failure. It says in the genetic, in the genetic mutation, it is known to occur in 20% of the population. Since it is occurring, it means it's a yes, it is in the human, and that is 20%. This is same as 0.2. This means that those that does not occur, failure will be 80, or that is 1 minus p. That is 80%, that is 0.8. That is how you find the equivalent failure. That is not all the information. The scientists did a survey on 5 people randomly. So people is 0 to 5 randomly. The question is, what is the probability distribution of the number of people who have this mutation? What is the probability distribution of the number of people who have this mutation? What are we asked to solve? We are asked to find probability of people having a mutation, or you're asked to predict the likelihood of people getting this mutation. Probability, likelihood are the same. And this is in the field of epidemiology, that's spread of disease in the population. Okay, so let's see how we are going to solve this preamble. How do we apply our binomial theorem? In statistics, we have something called binomial probability or binomial distribution. It is in that approach. In binomial probability, there are certain things we want to look out for. One is the number of trials. Number of trials is like the survey we did. It was 5 people we tested. Probability of success was the p, given as 0.2. What is the failure rate? It was kill. We are using kill, and that was 0.8. Number of success is, we are looking at the probability that X people will have this image, probability that no one will have it, probability that 1 person has it, probability that 2 people have it, in the given number 5. And so what's the probability of the mutation being equal to some X number of people? So I'm using K equal to X. That is what we are looking for. And so this is how we are going to apply the binomial theorem. We know p plus q to the power n is given as, I always want the other way around, n minus k, k. I love it this way. You know this is the same as saying a plus b to the power n. So it means my A is K, my B is the Q. You are using this if you think PQ might be confusing. Okay, I'm helping you to solve the problem. So the question, what is my N? My N is 5 people. My A is 0.2. My B is 0.8. Summation K running from 0 to 5 now. What's the probability that K is 0? What's the probability that K is 1? Probability that K is equal to 2? And so on and so forth. We want to find probability of 0 means no one is getting the mutation in the 5 sampled people. 1 means only one person has the mutation. This means only 2 people have the mutation up to when all of them will have the mutation. So how would you solve this? I know at K equals 0, that is 5 combination 0, 0.2 raised to the power 5, 0.8 raised to the power 0. What is the answer here? If only one person is getting the mutation, I know it's 5 combination 1, 0.2 to the power 4, 0.8 to the power 1. The index must add up to 5. These properties must hold. So let's find probability that no one has it. What is K as 0? Only one person has it. 2 people has it. 3 people have the permutation. K equal to 4 people. K equal to 5 people with the mutation. Let's find answers to this and then have it in our comment section. And that is how beautifully binomial theorem can be applied. With this problem of the day, you realize that we are looking for probability at each term, for each term. It wasn't for the whole expansion as we did in the previous example. We are looking at exactly K people having the mutation. If that is done, it means we are looking at specific terms in the expansion. You would realize it. We are looking for K at 0, K at 1, K at 2, K at 5. When you are looking for specific terms, it means you are looking at terms in the binomial expansion. And that will be the third sub outline for us to consider, which I'll make the lecture video on that separately. And so you want to take your time, go through what I have done, and then you understand it and appreciate it. Again, if not subscribed to this channel, you want to gladly do so for more lecture videos. Simple to understand. Thank you and see you in the next section.